Very much. Okay, so thanks, you guys. So I gave a talk this morning, and I don't know if who saw my talk this morning. Okay, good. So there's some people that didn't. So I'm going to repeat a few things, but not. I'll try to be a little bit different, hopefully. So anyway, I just want to start with this slide again. Just to repeat, the guys that were here this morning, bear with me, but you need to learn some more stuff about transistors. I think you guys, all your software guys out there knew about transistors at one time, right? Every engineer had to take like device physics class, right? Okay. So I just I just wanted to just go through this one more time because I think this is really important. At least for me, it is. I mean, this is really exciting stuff for me. So anyway, that thing on the top is a transistor, right? Drain. What's the gate's the middle part, the middle bit, and that's what turns the thing on and off. And you guys deal with ones and zeros only, so that's a good thing, I guess. And then the bottom one or the middle one shows an actual picture of a transistor. This is on one of our 40 nanometer devices. So you see that thing says 35 nanometers. Really, it's kind of 40. It's hard to measure that, but that means that's the process node idea. When you always hear about what process you're in, it's always about the how fine of lines you can draw, right? And so 35 nanometers for this one, and then the one on the very bottom. I don't know if you can see it. I'm going to jump down here because I think it's pretty cool. So. This, so you're like, oh, you think, oh, here's the gate, right? Here's a tungsten silicide thing, right? That's like a piece of metal. And then we have what's called polysilicon, which is, polysilicon always means it's conductive, right? So, so that this whole thing, this whole thing that sits on top of the actual gate, the gate's like right here, teeny tiny thing. You can't even see it when you look at it this way, but when you blow it up, you can count atoms on here. It's so thin right now, which is totally amazing because we have to make it thin in order to control the electrons that flow through this channel, right? We want to be able to turn those things on and off effectively. We want to go fast because you software guys always want to go faster, right? We can never go fast enough. So the idea is making these gate oxides really, really thin. So this is in 40 right here, and I'm working on stuff now that's in 28 FDSOI. And you hear this in the news all the time. I have a story from my son. So when he was a little kid, he liked to play games in the PlayStation, and he tells me, he goes, "Dad, the new PlayStation's coming out, and it's like I can't remember the exact, it's in 40 nanometer FD, silicon on insulator. Isn't that awesome?" I go, "Do you know what that means?" "No, but it's awesome because they're telling me it's awesome," right? So, which I thought was really funny. So, but the idea is, that we can do in 28, I think it's bringing those to the general market is really interesting for me. Like it's changing the world. Things that we can do. Like there was a talk this morning about voice. Who would have thought that I could in my house have an echo thing that I could say, "Oh, Alexa, please turn my lights on." I never would have thought I would have that. I would never have thought I drove an electric car either. But anyway, I think it's changing. It's not that good yet, right? It's not so natural language yet, but that's coming. And it's all because of this idea that the process nodes are getting deeper and deeper. And you always hear about Moore's law, and this is an example of it. So right now we're at about 3 million gates, 3 million gates per square millimeter. So this M4 is about 0.1 square millimeters in that 28 nanometer node. So I mean, 0.1 square millimeters. Does that mean anything to you guys? That I can put like a typical die size of like I shouldn't say this exactly, but anyway, die size range 10 to 20 square millimeters. 0.1, I could put like 100, and you wouldn't even it's just so small. So anyway, just want to explain that a little bit. And it really will change the world, I think. Anyway, so this just tells you what we're doing, and I just talked about this already, and I'll skip through some of this stuff a little bit more. I just want to talk about this one more time. I don't think I explained this so well this morning. I always get this all the time. And I talked about like, I need to do this, this, and this with my system. So now, and this happened to me. This happened to me last week. I was at a customer, and they want to do this thing, and they're telling me, I need quad A53s, and I have to run at 2 gigahertz to do this thing I'm doing. And I want it to cost $2, by the way, and I want to run a 200 milliamp hour battery for 10 days. I go, first of all, that's not going to work. This is not going to work, because what they do is they develop all their stuff on a PC, right? All their algorithm on a PC, and they transfer it over to an i.MX part, right? And it's like, And it's like it's like, oh, come on, software guys, please. You know, we have to get a little creative on what we're doing because, in order to meet your price targets and your performance targets, we have to do something different. So let's think a little bit differently. So let's think different. So that creates this. How many minutes do I have, Robert? You need to talk. Plenty. Okay. So anyway, so we have to think a little bit differently. And I work with this older architect guy at a pretty big company. I think he's in his late 60s. I'm getting old too. I'll tell you another story about that. I'm getting old too, but he always tells me, oh, we've done that before, Rob. There's nothing new you can tell me. I go, yeah, okay, well, we're going to do it a little bit differently. Another funny side story. I'm walking through the Smithsonian Institute, a space science museum, and I'm turning the corner, and in this museum is a satellite I worked on. I was like, oh my God, it's like, am I getting old? I can't believe it. So anyway, that goes back to my experience with satellites. We used to use a lot of different processors. Like as an example, the data handling computer had a bunch of different micro Cs in it to control, like had a command receiver, telemetry encoders, or for transmitting, and also had, just like, like this guy says, you're not doing anything new. So we had gyros, sun sensors, star trackers, earth sensors, momentum wheels, which are momentum wheels, which control attitude. All that stuff went into a sensor hub. So that we call them sensor hubs now, but that was done a long time ago, and it was done with separate, sensor micro C things, right? So now when you go to, Apple comes out with their new phone and they announce we have an M7 now. How awesome is that? And everybody says, wow, that's cool. They don't even know what it's for or why, but it's cool, right? So the same idea, right? It's got the gyros, but now they're digital. They're not like this is a motor one, and so now we all have. MEMS ones, and then we have a sensor hub. Application processing completely off, right? Completely off, and it can do all the sensor data calculations. It can do all the Kalman filters and things like that to do motion tracking. So all the inertial navigation now can be done in this little thing, not on the big thing, right? So that's way better. It's way better, and that's kind of going back to what was done in the past. And I always think about our brain, right? I always think about this as like we can sleep and we can still breathe, right? I told my boss that you should never talk about like this, but I think it's kind of funny. Our stomach has a brain too, right? It's like it's telling my brain I'm hungry, so there's something in there that's got some smarts to it, right? It's not my brain telling my stomach's telling my brain I'm hungry, right? So we have all kinds of different processing units in our brain. So kind of following this, evolution, we should look at evolution. It's been there for so long, and it's been optimizing. Our brains are so incredibly intelligent. Let's take some of that knowledge and put it into our systems, right? So then this brings me back to this whole idea. This heterogeneous idea, and I put this up here because I don't know what it means. So it's just so you know, it means diverse and varied content, right? Diverse and varied content. And I looked it up, this heterogeneous processing, and this was used first in 1960 by Burroughs on one of their mainframes, and they were doing very similar things. So now we can do this in one piece of silicon. So, so going back to the point, why are we doing this? It's like we're trying to say we're going to save power, we're going to optimize systems, and how can we do something a little bit different? How can we give the software guys other options to lower power, to improve systems performance, instead of saying, oh, I need a 2 gigahertz, Cortex M4 to do my thing, right? So, but I'll go to the punchline first. It's a challenge, right? I talked about this to somebody I can't remember who it was today. Every time we've introduced this to a customer, we have like one design team that does Linux, right? And then Linux, where's my shell? They don't even know, most Linux guys don't even know about debug tools. DS5, what's that? We don't even use it, right? Just shell, right? Now if you put an M4 in there, well, there is no shell. You can do it, but there is no shell. You have to use debug tools. It's a little bit different thinking than the Linux guys. And another story I can tell. I met a customer. I guess I can tell you this. Yeah, I can tell you this. Well, maybe I shouldn't. Hang on. I won't tell you who it is. But anyway, so I can't believe this thing that they're making. They use a Linux processor for it. I just couldn't believe it. And then I said, well, you can do the same thing with an M4. Same thing. And then this guy was an architect guy. And then he brings his software guy. He goes, well, I can't use it. There's no shell. I go, oh God, okay. So that was like, it was a challenge. You're paying double, more than double for your system with memory, PMIX, and all this other stuff, and you could do it much cheaper, but you don't have a shell. Okay, I won't argue. You're the customer. So anyway, my point is, we'll give you more stuff, but I worry about how we're going to implement, and having us provide frameworks for that to happen, and even like this idea behind Qt, being able to have some kind of abstraction into this would be really good. And I think working with companies like Qt will help evangelize what we're trying to do. So anyway, so there's different ways to do this. Adding cores. The idea, like if you look at, thanks.
I'll do this.
Oh, thank you.
It's painful watching you go up and down.
I know. So anyway, so I think like the idea of I lost my train of thought. Anyway, so
If I can.
yeah. The idea of heterogeneous versus like symmetric processing, everybody's used to that, I think. If you look at Intel, when I first bought my computer, I think 500 megahertz, going gigahertz, blah, 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 and then they're kind of plateaued out at about 3 or so. What are they starting doing? Oh, quad core, and blah, blah, blah. They're getting lots of cores, right? But that's more symmetrical processing, right? So one operating system distributing a task amongst cores. For this idea, it's a little bit different than that. So anyway, so this is an implementation we have on our SX. You can buy this right now. You can start trying things out if you needed to. I would hope people would try this out. And we have an M4, and we have an A9. A9 can run at 1 gigahertz. This M4 has direct access to all these memories. You can even shut all this other stuff down, not necessarily power-wise, somewhat a little bit. But it's a pretty good start, right? But it's like if you look at it like I do in the picture, is that those 2 cores have access to the full matrix. So what that means is that this guy can have access to this memory. It can have access to quad spies, all these low-speed peripherals, all this stuff. And the way I draw these drawings, I think, to help people a little bit to understand how things work. And the other thing is, like, when I first came to Freescale, it's like all these words they use, it's like they make them all up. And the customers, like, we have OC RAM. What's OC RAM? Do you know what that is? OC RAM? On-chip RAM. Well, where else would it be? I don't know. So we make up these words, and it's like it confuses people. Like, we have guys talking like, and nobody knows. You know what they're talking about? No. So anyway, so trying to be more clear on terminology. So we have this 64K RAM here associated with the M4, and we call that in our vernacular TCM RAM, so tightly coupled memory. But it's just RAM, right? And it goes through one layer of bus matrix, so it has like 1 clock to get there. If I look here, it's like that's like 2 or 3 clocks for each bus matrix, so that's 6 clocks or so. So that's a lot of clocks to get there. So we have a cache on board, so it kind of minimizes that latency penalty. So having a cache is important with an M4. And I always thought that was kind of weird too. It doesn't make sense to have a cache on a real-time thing. Anyway, so anyway, we're changing that on our newer products. But this is the SX. Go to the next one. So on the 7D, we just came out with this about 6 months ago, and this is in 28 LPP, high K metal gate. What does that mean? It means that it's going to be lower power for you guys. So the gates are not polysilicon anymore; they're actually metal. So it's a much better way to get fields into the channel. So this is a little bit different architecture. The M4 now sits on this fast domain, so it can go super fast, but it still has access to everything else. Okay, go to the next one. So I'm going a little bit fast here because I don't have a whole lot of time. Robert wants to talk. So anyway, I just want to talk about the advantages. So like, when I say cycles to access a peripheral, A9 takes 92 cycles to get to a pin. If I wanted to toggle a pin, it takes 92 cycles, right? So if I wanted to toggle that pin at 10 megahertz, that means multiply by 100, right? That means I'd have to operate this thing 100, no, 10, no more than that, 100, yeah, 100. So to get a 10 megahertz clock toggle, I have to go 100 times in frequency of the core. So that means gigahertz, right? I mean, it's insane. It's insane. Why do I have to go that fast just to toggle these pins? So the M4 is on this part is much less cycles, so you can lower the frequency a lot. On next generation stuff I'm working on, this will be 1 cycle for the M4 to access those things, right? So much more efficient, much more efficient. And then this kind of shows total system power, 235 milliwatts to do a particular task versus 70 for the M4. So you can kind of see it makes a big difference. So next one. Okay, and this describes like the power differences between so you can see just like looking at this, I think it's interesting for me. It tells a lot, this picture. So this blue line is in 28 nanometer. This red line's in 40. So the slope means the process difference, because the capacitance of 28 is significantly less than 40, and it goes 1/2 CV squared for the power. So you can see the difference in process. This offset here, that indicates how we did it. Like we put on the SX, we put it in a low power domain that had a lot lower power, and where on the 7D it's a little bit higher power domain with more leakage. So that's why I have that offset. So this picture tells a lot to me. So anyway, that's kind of interesting. Next slide. Yeah, the only thing I wanted to talk about this one was just the performance. Like I talked about TCRM. This OC, just to let you know what the names meant. So TCM is that tightly coupled one. Cache on and off, it doesn't make any difference at all in performance, core mark performance. That's the workload we use. And then if you look at from other RAMs on the chip, without the cache on, it's really bad. And then if I put the cache on, it's almost the same as running out of the TCMs. And then we can also run out of DDR, and DDR is a bursty memory, right? So without the cache, it's 0.19, and with the cache on, it's 2.24. And then also we can execute out of quad spies. So it kind of tells you the importance of having a cache with that part. Okay, so that's that one. Let me see what the next slide is. I can't see. Go next one.
I'm trying.
Oh, is it having problems?
Yeah.
Oh dear. Really? It's stuck?
There we go.
Okay, so now I'll go through these pretty fast. I don't have that much time. So the idea is, okay, now we have all these cores. How do you deal with partitioning them? As far as like peripherals and things like that. And how do I do the messaging? I'll just talk to this, and then you can have it next. So we have this messaging unit that is really a bunch of FIFOs and flags that each core can talk to each other with. There's also a semaphore unit that you can set semaphores to share things. We have this thing called resource domain controller that you can partition. Like let's say you have on this system you have 5 UARTs, right? And I want 2 UARTs for the M4 and I want 3 UARTs for the A9. So now you can set up this partitioning unit that says, okay, M4 you have access to this and you have access to that. If the A9 try to get to the M4 stuff, you get a memory board. So it makes it kind of safe, right? So anyway, I'll finish up. The rest of it is all just blah blah. So anyway, more detail of how we did those things. So
okay.
So and nobody reads the user manual anyway. And so these are in our Linux ports. So I'll give you you got it, Mike?
I'm going to use this.
Oh, okay. So thanks very much.
I can't run around as much as you.
That's right.
So we just wanted to spend the last 5 minutes. So Rob's talked about the theory. I think the big difference between NXP and a lot of our competitors is the availability of boards, which obviously you need. So what we do as a company, for each part we release one. This is our target platform that we use for testing for our Android and Linux BSPs that we maintain across for all our parts. It's a general purpose board. It's not aimed to be cost sensitive or really to be optimized to any of the target markets we go after. It sells for $149. It's open source. We give you all the files to go along with it. But really, if you look at the i.MX7 and a lot of what Rob is talking about in terms of low power, it's not optimized for a final design. So what we also do is we try and come up with some more designs which are really more form factor aimed at this wonderful world of IoT and wearables. So this is a reference design that we developed with a partner Element 14. It's called Warp 7. It's really, as you can see, it's sized optimized. So if you're designing something that is going to be an IoT product or a wearable product, the main board, the CPU board, is 38 by 16 millimeters. So you do not have to redesign it to fit into your final product. Again, this is purely totally open source, so we give you the Gerbers, the schematics, the CAD files. We're not trying to hide anything. It's open source hardware and software. It runs Linux. We will be coming out with a version of Android. We're working with Qt to get Qt Lite running on this when it's available with 5.8. So again, this is something we do to really help you get to market as quick as possible. Again, this is purely open source. It sells for $90. It's available today through Element 14 website worldwide. It doesn't matter where you are. And again, we're just trying to show, Rob's talked about a lot of the capabilities of the i.MX7. Really, we want to give you those capabilities in a form factor that will allow you to go to market very quickly. Okay, so that's what we're trying to do here. It's small, but we pack a lot onto it. So this is, I'm sure, block diagram, and these slides are all available. As I said, this is all open source, so we have nothing to hide. You have the i.MX7 there, but on the main CPU board, it has DDR and flash memory in an MCP package. It has a Wi-Fi Bluetooth module. We work with Murata, the same module that was used in the iPhone 5 or 6, I believe, which is now available. And then, as you can see from the baseboard, it's a two-board design. We've put a lot of the sensors for you to experiment with in terms of usage models for your final product on the baseboard. It has a battery. The actual product looks like this when you purchase it. It comes with the two boards, obviously the connect to the battery, and the expansion header, which you can see on the I/O board, is for click modules, and there's about 200 of these click modules, which allow you to experiment with different sensors, with different different ideas in terms of a product. So again, these click modules are available for about $15. So what you can do is you can use the Warp 7 as a basis for your prototyping. You can buy these click modules, and you can really experiment with a wide variety of different usage models for very different markets. As we know, IoT is just a catch-all term because we don't know what we're talking about. Nobody knows where the money is. So all we're doing is trying to give you a way to get to the money as quick as possible. In terms of the software ecosystem, we took our Linux BSP, which is based on Yocto. We adapted it for the board. We're coming out with Android. We give you U-boot and Yocto, so this is all mainline. It's all available today on the Element 14/Warp 7 website. You can go there. We've created a GitHub as well, specifically for the Warp 7, so all the code is available, as with all our BSPs. And we have the documentation that's on the GitHub as well that's all ready to go. And behind that, we also we have a community because this is all open source. So if you go to the website, you'll see a community. People are purchasing them, beginning to play around with them. Today, we don't have a display for it. We're trying to lock in supply of a display, which will be about 1.54-inch display, so it will be form factor compliant. So again, you can understand how QtLite or the UI of your choice will be in that form factor relevant to your IoT or wearable product. So that's the way we enable NXP ourselves, but we also, I forgot to mention, every part we used is available through all the major distributors. So what we don't like is, there's a lot of reference designs on the market where you go through concept and prototyping, then you want to go into production, and you find that half the parts aren't available unless you're buying in 100,000 quantities. So every part on the Warp 7, we made sure it's available in low volume quantities through all the major distributors in a worldwide basis. We published the BOM, so the bill of materials is on the website, so you can see what parts we used. It has the manufacturer's part number and the distributor's part number. So really what we're trying to do here is similar to Qt, we're trying to get you to market as quick as possible with all your wonderful products. Now, that's part of our ecosystem. What we also do is work with a number of partners, because like any company, we can only support a certain number of companies direct. So we work with a lot of partners to enable them to get their boards up and running, and they can support many different markets. So I'll run through a few very quickly as I run out of time. So Boundary Devices, they came up with a single board computer. They're obviously looking again at the industrial market. Remember, this part, it has a longevity, so it's going to be in the market for at least 10 years. So if you're looking for a long life cycle product, Boundary Devices, a single board computer, is a very good company to work with. So we also work with Toradex, who came up with a system on module. So the Warp 7 is obviously optimized for a very small form factor. If you look at where a lot of the market going is, people are beginning to develop system on modules, not single board computers. So a lot of our partners now, you can go back to them. If you're looking to do a production run of 1 to 5,000, you can buy the SOMs directly from our partners. So you don't have to go to a contract manufacturer, go through negotiations of how you're going to get into production. You can go back to a company like Toradex and buy your SOM in volume and get to production as quick as possible. Obviously, Toradex, they're based both here in the US and Europe. We have partners such as Technexion that are based in Taiwan. They have their own manufacturing capabilities. So again, they came out with a very small module based on the i.MX7. Again, you don't have to worry about DDR layout, flash, what Wi-Fi Bluetooth module, how you're going to connect it. That SOM is already fully designed. You don't have to touch it. You can go back and buy from them in volume. They're also a contract manufacturer, so they can actually get you to market working with one company the whole way. Couple more, Israeli Computex, the same, Computex, CompuLab, it's too late in the day, is an Israeli company, very similar form factor. And then Phytech is another company that we work with in Europe. And then finally, even the distributors have got into the game. So we worked with Arrow, and Arrow developed their own i.MX7 based board around the 96 boards initiative from Lenaro. So really what we try and do is we try and take all the smart work from people like Rob, and we make sure that if you're interested, there's a wide variety of boards that you can go and buy. You don't have to buy the NXP boards. We actually prefer, if you buy our partner boards, because they can support you and get you to market probably faster, because we're only one company, we can't support thousands and thousands of customers. And we are out of time. Thank you for your attention.